by the way, we'll also have a new YouTube channel because I'm finding it difficult to manage all the links. So I figured out how to create a YouTube channel. So we'll have a YouTube channel. Okay, right. And so the cool thing is that since some of you are also in the business of scheduling stuff, this when to meet website is a much more, I find, less daunting alternative to Doodle, which is what everybody else is using. I started using that. Obviously, you don't have to adopt it. So basically, indicate, please indicate your availability Monday, Friday, 9 to 1 a.m. Okay. All right, let's see what else. Let me go with my email because it's trying to dump everything there. So homework 5 is due a week from now. I mean, you've had it partially, you've had it partially assigned for at least a week now. And again, it's another example of me falling behind. So you should look at it and you should ask me questions today. We're going to finish the lecture today with basically a review, just an overview of that homework. And like I said, this homework is aimed at the people who are signed up for 443, and people who are signed up for 442 will get their own homework tomorrow. Okay. Okay, I think that's all I had in the email. So as I said, going forward will differentiate between physics 442 and 443. I.e. separate homeworks. I mean, obviously, if you want to do both sets of homeworks, that should be 3 times the fun for you. Okay, so last thing, I benefited greatly from having conversations with 2 or 3 of you, maybe 3 or 4, I forget, because I'm just realizing that in this format, it's very easy for me to forget that I have a class to teach and forget about what it is that I'm doing or not doing. And having a more, and especially since most of you, appear as black holes on my screen or black squares with your names on it and mic crossed off. It's very easy for me, like we all talk about how easy it is for students to disengage and how most of them disengage from classes, but it's actually the flip side of that is even worse, right? It's very easy for me to disengage from the class. And so what I've decided is that, especially in cases where, I haven't seen some of you and I haven't seen some of your homeworks, and there's 3 of you who have not turned in enough homeworks, and I'm worried, right? So I'm going to make mandatory office hours. Basically, please email me. Please let me know. Let me know by email or Slack when we can meet and discuss your homeworks, independent reading proposal, or anything else.
Professor, you want to do this at an individual level or everyone?
If we haven't, if you and I haven't met or haven't discussed it, basically I want to make sure that I've availed myself to office hours. About 3 of you took me up on that, and we've had impromptu office hours on weekends or random times, just ad hoc scheduled by Slack. But most of you at best have just submitted the homeworks.
Yeah.
Like I said, it really helps me to know whether you think you're getting what you need to get out of this class, or what's the difficult thing. What can I, sometimes the fixes are very easy. Sometimes they require rethinking things. So for example, this, my new sort of idea of differentiating between 442 and 443 came as a direct outcome of having a couple of these conversations and realizing that there are people in the class who need to have some basic knowledge of how quantum mechanics works, not just as principles, which is what we covered, but actually working out a few differential equations. Okay. That's standard content. So my idea is that, if you haven't come for the office hours, actually, as a default, please let me know when we can meet in the next, say, week for, I don't know, 5 or 10 minute chat. It's not, for all you know, you need advisement anyway. We can combine advisement and discussion.
Oh yeah, I need that too, actually.
Yeah. No, I think also, right. So I keep remembering things I should have told you. This week, please. This week, please. And guess what? I'm gonna bug you if you don't email me today with some proposed meeting times. I'm gonna bug you individually, not in a mass mailing, but I'm gonna email you, because I feel like it's important to kind of like just make sure that we're all staying engaged in this. So there were a few of you who were interested in career advice, because since you're graduating, there's roughly half of you upper seniors. So there's a physics club, or so-called physics and astronomy club, FAST club meeting, 3 p.m. What's the date? 4/22, right? And again, I think all of you had emails about it from me or Justin Peterkin. See email announcement. Now, to update you on what's going on, the idea is that Charles Liu and I and a few other people will kind of just have an open discussion and hopefully answering some of your questions about what a physics degree is good for. So of the other people who are going to join, there's going to be Sharon Laverde from chemistry. She has a physics PhD and she went into the chemistry field. There's Tobias Schaefer, who some of you sure know. He is probably the most interdisciplinary of the four of us, because he's done research on finance, he's done industrial research. He's also a physics PhD. I'm also probably hopefully going to find some of the CSI alumni who went into the industry, who work for companies. That I can't guarantee. Those people tend to be busy. But the idea somehow is to make this an ongoing sort of a exchange where there's so physics is only second to math as far as its versatility, right? And that makes it very difficult for you to have the big picture of where one can go with a physics degree. And okay, so the idea is to actually tackle this. It's difficult for me to actually summarize all of these options because I only know one. Anyway, so all right, this is already getting off topic. Let's get back to the topic of this class. Okay, I think this is more than enough organizational things now. So the plan for today, so the one of them was to deal with organizational stuff. How much time? Oh boy. So the other part of the plan today is finish Simon's algorithm. Start basic, or I should say basic, I should just say start quantum mechanics in 1D. This is physics 442 stuff. And for those of you who've taken it, I've actually, in the interest of trying to entice you to listen on as a part of your review, I will try as much as possible to use examples that are fresh. They're not standard examples in textbooks. But I also, they're simpler, right? So the idea is that because I have less time, I'm going to use examples that illustrate points, but with less math. So I'm going to start on that. If I don't finish it, I'll make a recording and post that. Okay. All right. So actually, let me do one thing real quick. If I have that. Yeah, since I promised that, let me just do that real quick now. Let me share with you okay. So this is the final version of homework 5. There's no chance you guys should just, had a chance to look at it. So the first 3 problems, or so-called problems, are easy. You basically go through Qiskit, you make sure you can get things to work. There are little exercises of problems at the end. You answer them. They're not real problems, but anyway, they have questions. You answer them. You take screenshots. You save them, paste them into your Word or something, and that's the done thing. Problem 4 is basically go through the Deutsch algorithm step by step for this particular function, which, okay, pop quiz, is this a constant function or a balanced function? Should we take a vote on that? Let's do a poll. I'm feeling frisky. Oh, of course, it's going to not let me do that. Okay. Pop quiz. Is this a constant or balanced? Let's see if it's going to let me do this. All right. So I'll continue talking whilst the poll is running. Come on, guys, vote. So for this function, the idea is that you will write out, and I think Qiskit actually goes through a version of this because they're so detailed, but you will go through and write out the matrices that are needed to implement the Deutsch algorithm, including the oracle, the function itself. But the idea of thinking about it step by step as a debugging sort of a, oh, whoops. Sorry, I goofed on the poll. The poll should have not been yes or no, but rather which one it is. I apologize. 1 second. Let me fix it. I'm very sorry, guys. Is this a constant function? No. What annoying that. All right, let's try this again. Yeah, so the debugging mode basically means that you run, you write out everything that happens at each step. Now, this problem is the only real problem, I would say. And it's a real problem in the sense that it requires thinking, it requires, and this will prepare you to running, for running real Qiskit programs. The idea is that, there's no such thing as an ideal measurement. And so if you examine the way these algorithms work, even when the claim is that, oh, you're going to get the answer in 1 shot, which is what the Deutsch-Josse algorithm promises you, or the Deutsch algorithm. The idea now is that suppose you're dealing with a real computer, and every time you want to measure a zero, you're only going to, every time you should measure a zero, you'll measure it a zero, but only 99 times out of 100, for example, as in this problem. So it turns out, as you will discover, that if you have little errors like this, 99% is pretty good, right? But if you have little errors like this, they add up real quick. In fact, they multiply because these are probabilities. And what you'll find is that by the time you're up to a 20 qubit calculation, your errors will be pretty significant. And so in real life, and I hope I put in the hints, in real life, the way you deal with this, as long as errors don't blow up too much, you can deal with it by repeating the run, because quantum mechanics is deterministic. And so if I were you, I would try the most difficult problem first, okay, which is this one, and let me know how that goes. So I'll bug you again tomorrow or Wednesday to see if you've done that. Anyway, the last problem again is testing to see how well you know linear algebra. Essentially, it's not a quantum mechanics problem. All right, let's get back to. Oh, I should look at the poll. Did I launch the poll? Huh. No, that's so if a function which is f of 0 is 1 and f of 1 is 0 is not a constant function. So those 4 of you who said that it's a constant function are either asleep or well, you're wrong for sure, but I'm curious why you're wrong. I think that's pretty important to figure out why you're wrong. I'll leave it up to you. We can talk about that during.
I just guessed because I don't remember.
Oh, but doesn't so one of the most useful advices about math that I can pass on from a person that I admire a lot from grad school is that in physics, physicists are extremely impatient. They just name stuff just to hang a tag on it so they can move on, because things are pretty they're just impatient by their nature, right? I mean, obviously we have some patient physicists around as well. But mathematicians are just the opposite. So when they work on new things, they never rush. They think of names that properly encode what they're talking about. Because, in physics, you have things like beta function. Why is it beta? Because they used alpha in their scratch notes and they needed the next letter. I mean, beta functions are kind of important sort of a function that you compute in renormalization group, for instance. But mathematicians, when they say a constant function, they really mean the function is the same, right? Balance is more of a jargon. That's why I put in constant function. So anyway, so the fact that this function was 0 for one input and 1 for the other input is a giveaway. Anyway, it's fine. Yeah, I'm not judging you. Even if I sound like I am, I'm not judging you. Let's keep going. All right, so let's now switch to, I need to find my cheat sheet. Okay. All right, we're done planning. Let's jump into it. Finally. Oh my God, I really need to skip on this. So quick reminder, some common features, right? So there are two basic, I should say reminders. Two basic moving parts in quantum algorithms so far. So one of them is load up a superposition of inputs to enable, I'll put it in quotation marks because it's a little it's a bit more intuitive than I like. Parallel processing, right? So what I mean by that is that you've got registers that are initialized classically in zeros, and most of, well, actually all quantum algorithms that we've seen so far start with applying Hadamard operations to all of them, right? So outcome of this is basically a superposition, as we discussed, of all possible strings. X is 0, 1 to the end. So that's one common ingredient. The other one is less, it takes longer to explain. This is very intuitive. The other one has been pretty common, which is a phase kickback trick. It's a trick of sorts. And that basically allows you to, the reason why we need a phase kickback is because, the idea is that we've got a register that has the inputs and there's the outputs. So there are outputs here and there are inputs here, right? And these are all inputs. And usually what we do is that we imagine that there will be a some kind of a function that takes the inputs and produces for us and updates the output register. That's the way we think about the function. The trouble is that if your inputs are made up of a vast superposition of all possible inputs, the outputs will come out to be a noise. If done carelessly, which is, I think we've seen at least one carelessly, the output is all noise. And for the Deutsch problem, let's see, instead of writing this out, I should just do copy and paste, but right. So the idea somehow is that if you consider X, Y, so we'll start by putting the input register into superposition and Y into 0, for example, then you can see that the output, so for example, if you apply a C0 gate to this, or whatever, controlled the UF, the output will be let's see, which function do I want to use? Yeah, let's use C0 actually. That's what I have in my notes. That's kind of an example. The output will be 0, 0 plus 1, 1. Right. And so you can see that the outputs are all mixed up. Right. This is actually explained in the book pretty well before they do the Deutsch algorithm. So instead, you can see that it's crucial to have a particular superposition on the output, which has this effect that the 0, 1 operated on UF has this effect of kicking back the phase onto this is something that one needs to, oh, come on, this is not going to fit. Let me move it here. Sorry, one of my computers is wheezing. Maybe this is too much. Just try it. Right. Plus times 0. So I'll confess that we've worked this out more than once, and I've repeated more than once, and partly the reason for that is because I have not come up with a nice intuitive way of thinking about this. This is just math. And what it does is that, you're right. So I'll remind you that the way this works is that basically the target bit in this particular superposition is left untouched by the operation, but it transfers the results of the operation onto the control bits themselves. And that's extremely unusual from the point of view of classical sort of computation. And like I said, other than doing the math, I don't know of another way of explaining that. Right, so those are the two ingredients so far, and they've been used in Deutsch, which we covered, Deutsch-Josa, which we also covered. So Bernstein-Vazirani, I'm going to, because I'm running out of time, I'm going to just give you my notes, because it's a two-line derivation, which basically says use Deutsch-Josa circuit, but feed S state. Well, not feed. The output. So okay, actually, let me remind you what Bernstein-Vazirani problem is. I don't want to. So you know what? Since I have notes on this, maybe I should walk through this. Okay, let's do it. I didn't want to do this, but here. I'm just realizing that I'm not writing fast enough. Okay, so yeah, let me skip Deutsch-Josa. So let me focus on Bernstein-Vazirani. Okay. So Bernstein-Vazirani basically says, suppose there is a function which is just a linear function, s dot x mod 2. The point is that we want to know what s is, and classically it takes n calls to figure it out. Now, if we look at the Deutsch-Josa circuit, which I drew somewhere up here, okay, which we covered last time, and if this function is acting in the circuit, you can see that, if you just use the formula that we derived last time, you can see that after operating with this function, this is sort of an example of debugging sort of a view of how these algorithms work. If you write down the state after every operation, and the way Kayla Flum, Mosca, and Kiskett, they chew it out, this is the state afterwards. But what you know is that if you just operate on the state with the Hadamard transpose, then it'll just produce a bit string, which is S directly. And the way you know this is because the square of the Hadamard transform is the identity, right? You know that if you apply it twice, you get the identity, but this state that you get after, these stages of the algorithm, which you have to just basically go back and look at your notes, and you can look at my notes or rewatch the lecture. And I'm probably going to, I'm going to have to record this separately, probably. You can convince yourself that the output of that circuit with that function is just the bit string itself. And so the thing to internalize here is that Bernstein-Vazirani is a very simple classical problem, in the sense that it takes, if these bit strings are length n, it takes n classical evaluations. So it's not a complicated, exponentially difficult problem to sample. It's only n. But it's kind of a cute demonstration that with quantum, if you have a quantum computer available, you can do this in one go. Just read out the. Okay. So now let me switch again to writing myself, because now I'm going to explain to you something new. Oh, whoops, now it's not letting me share the screen. That's weird. There we go. Okay. Okay. So now in the remaining 20 minutes, let me carefully go through the assignment problem, because that was sort of the main thing that's left. Algorithm. Okay, so there are several things that are, let me first define the problem, right? And the reason why we want to talk about this problem is that it differs from the Deutsch problem in many regards. First of all, the function that we're going to be interested in is a function from bit strings to bit strings. It's not from bit strings to bits, right? Remember that the in Deutsch problem, the function was just you feed it any string, it spits out a bit. And we are told that f is either 1-to-1 or, and that's sort of the more interesting case, 2-to-1. So that there's the mystery string that if you take an input and do and add to it that string, right? You can see that x is generally not equal to x unless s is of course 0, but the function is the same. And that's sort of like what you expect, for example, if you have a parabola, right? If the operation is that x goes to minus x, f of x is the same. So it's kind of like the same, all 2-to-1 functions are roughly speaking the same, right? Under some relabeling of inputs. Right, so this is the problem. So compute.
Professor.
Yeah.
Are you like writing on something?
Oh, whoops. It's not sharing. Oh my God. Yes, I have been writing. I apologize. Thanks for speaking up. Okay, do you see? Sorry, I had some, it's very strange why it's, you'd think that the learning curve would finally kick in, and I think it's partly because Zoom is a little bit unpredictable. Okay. So, so this is difficult. So you should realize that this is difficult classically. So classically, we need to call f, 2 to the n times to know if it's 2-to-1. Right, so this is horrendous. And being the length of the inputs. Okay, so now the question is, how do we do it quantum mechanically? So the crucial thing about the Simon algorithm, the Simon problem, you can see that it's already looking different. But the way the quantum algorithm works, it uses something else besides phase kickback. In fact, as far as I can see, it doesn't use any phase kickback. So it uses measurement as a device. So let me start just drawing. So some of the ingredients are the same. So there's going to be a, in fact, let me make some room. Input, and there's output. So there's an input register. Let me be slightly less sloppy and write 3 in, and this is going to be the output register. Okay. Now, since we're not designing it, we're just explaining it, I'm going to tell you that this is how it works. We're going to superpose the input like we always do. Then there's going to be function that operates. And now we want to ask about, suppose this function is 2 to 1, right? Then the output, and the notation that I used in my notes is psi sub a is after UF has been applied. You know, this is what we generally expect, that for each bit string. So now we're not using phase kickback here. In other words, because there's no 0 - 1 state on the output, you know, the output is always, sorry, Y, right? So if this is the Y register and this is the X register, the output is going to be Y plus f of X. Just reminding you of the notation. When we draw a box like that, that's what we mean. Because Y initially is a 0 state, right? Then we can skip writing that, right? So it's just X tensor product f of X, okay? Now, if the function is 2 to 1, there is a structure in the output that's imposed by the symmetry. Symmetry being that under action of S, you're taking F to F itself. Okay? So, and so if we run through this sum, you can see that different X's will give you the same f of X. And so we will just condense that in this fashion, okay? So that's the easy part. Now, X prime run over half of all states. Okay. Half being 2 to the n - 1, obviously. Okay. And so there, in fact, let me combine what I'm trying to say here. There are 2 to the n - 1 possible. So we assume that these functions are generic and what's the word? Balanced in some sense, in some n-dimensional sense. Possible outcomes of f of x prime, right? You can see what can happen, right? What can happen is that if the function is not 2 to 1, but 3 to 1 or 100 to 1, then there'll be a lot of degeneracies in this function that, you know, it basically looks like it keeps repeating itself. That might be an interesting case. That's not what we're talking about here. Right? Talking about just 2 to 1 functions. Anyhow, so at this point, what we want to do is we want to Hadamard it again. So let me remind you, recall this identity that at various points we've invoked, which is if you take a string and you apply a Hadamard transform to this string, you're going to get x s dot x, okay? So if your input state is all zeros, that's not a problem, right? Then you get, then that -1 gets dropped and you just get a superposition. But for any sort of a arbitrary, you know, input bit string, this is what we have. So now what we want to do is we want to apply h to the n acting on x. I'll insert that. So basically, well, actually, let me just write it. How do I do this? Maybe the best way to do this is just to copy the circuit, explain it with pictures. Let's see if I can do it without screwing up everything. Copy, paste. Okay, found that worked. Okay, good. Yeah, only partly worked. Okay, So now we're going to apply another. It's funny that circles are easier to draw than squares. Never noticed that. Okay. Okay. So far so good. Now the outcome here will be a bunch of things that look. So if you just apply this formula to that, you will have an outcome. So somebody's sending stuff in chat. Okay, no, that's no good. All right, you will have an outcome which contains stuff. Oh no, what's happening here? Okay, there we go. Which contains stuff. Let me just not make any mistakes now. X prime z. So there's a double sum, so I have to be, well, actually, no. Let me do it one term at a time because I think improvising, trying to improve notation is. So I'll pick one of these x1s. Right. And the point is, do I have the factors of 2? Yeah, good. Sum from z minus 1 x1 dot z plus minus 1 x1 plus s dot z. Okay. So what I've done is I've taken this formula. Sorry, I've taken this formula and I applied this Hadamard transform and just copied things. Okay. So now you see something that you can simplify. So far there's not much structure that we're using other than that there are these pairs of states that show up in the superposition. And so minus 1 x1 dot z 1 plus minus 1 s dot z z. Okay. Okay. So observe what happens to this multiplier. Okay. There are two possibilities because all of the, so s dot z really means s dot z mod 2. So it's either 0 or 1, right? So that basically tells you that this is either 0 or 1, right? The thing that so it's basically if s dot z is 0, then this is 2, and this is 0 if s dot z is 1. Okay. So what does that mean? That means that if we measure, so what do we want to measure? We want to know basically if one of these contributions shows up or doesn't. And what you see is that if s dot z is 1, then this particular bit string, the bit string string z is invisible, i.e. just, I think the term is destructively, what's the word? Destroyed by interference, I guess. I want to use the word destructive interference because that's a standard term, but destroyed by interference. Okay. All right. So the protocol now is that we want to measure what that pattern of Z is. And so the idea now is that if you think of the circuit, right, what we want to do is we want to measure, one of these guys, one of the outputs. You can see that what we've done is that we just picked one of these terms. So, whoops, remaining steps, all right. Remaining steps. Pick out one of the terms in the sum see if I can successfully copy it again. Next 5 minutes, copy. By measuring the output. Remember, the output is insanely noisy. By insanely, I mean, to emphasize this point that I flagged, is that there are 2 to the n-1 possible values of the output. Okay, this is exactly what killed the naive implementation of Deutsch, right? Because if you don't put the output into the 0-1 superposition, you'll get all possible outputs. Well, guess what? That's fine in this case, because the algorithm was designed to not use the output directly. Because once you've got one of these outputs and you've applied Hn to the one of these, you guaranteed once you measure this output, you'll measure one of them, right? But once you measure this output, this pattern is baked into every single input, every single outcome of the, say f of x1, right? So then you know that the input register is in this state, and if you apply a Hadamard superposition to this thing, you will observe the stuff that you observe is the stuff for which s.z is 0, and this is because of this orthogonality thing, right? Again, you could observe different z's, but they will all satisfy that, okay? And at this point, you realize that you learned something about this S, but not everything, right? S has n components. We need to repeat the algorithm n times or more. Let's come back to that. But suppose n times, and the idea is that you want to get a system of equations that looks like this by running the algorithm a bunch of times. Okay. Now, what do we try? What's the unknown here? Pop quiz. Sorry, it's easy to get lost in what you're trying to compute if, you know, there are too many steps. Anybody? So we're trying to solve for S, right? Okay. So if these equations that you're getting are independent, linearly independent, then how many equations do you need to solve for n components of S? Well, I already said n times, right? So this is sort of an example where with every run of the quantum algorithm, you learn a little piece of information about S, but it'll take you n times to learn all of the information, unless there are repeats, right? Unless you statistically get a repeated equation. But the idea, so this is how most quantum algorithms are generally sort of working, that you keep getting some pieces of information extremely efficiently, but the last step may have to be done classically. And so in this problem, basically, once you form this system of n equations, you can solve, I think it's called Gaussian elimination, is that right? Gaussian elimination by hand, necessary. No, not even with for the classical computer. All right. So that's basically the Simon's algorithm. And the crucial thing here is, again, counterintuitively, perhaps, that the output register does not output the answer. The answer is baked into the input register. And so this is different from phase kickback, but it's a simpler, you know, a similar sort of a theme, okay? All right, so I'm not happy with having rushed through it, so I'm probably gonna, I'm gonna share with you this recording, but I'm probably gonna record, re-record what I had in mind initially, which was a more sort of a careful review. And all right, that's a lot of promises. See if I can deliver today. Any questions? Okay, so let me check on something before I let you guys go, since all of you are here.